Hello everyone. Let's start with a puzzle. If I tell you that two triangles both have one side equal, can you claim they are identical? Probably not. Equality of just one side is not enough. Even if I add one angle along with one side, the triangles may still be different. For example, try drawing triangles with the same side length of 4 centimeters or with one side 4 centimeters and one angle 50 degrees. So, having one side equal or one side plus one angle equal does not guarantee congruence. We need something stronger, proper criteria with multiple equal parts in a specific arrangement. Let's explore one of the most powerful rules in triangle congruence, the side-angle-side or SAS criterion. Imagine you're comparing two triangles. If two sides and the included angle of one triangle are exactly equal to the corresponding two sides and the included angle of another triangle, then we can confidently say that triangles are congruent. This is captured in axiom 7.1, which states, if side AB equals side PQ, side AC equals side PR, and angle A equals angle P, then triangle ABC is congruent to triangle PQR. Notice how the angle must be the included angle, the one sitting between the two equal sides. SAS is so fundamental that it's accepted as an axiom, something we can't prove from earlier results, but must accept as a fact. Now look at the example on the slide. Both triangles have one side equal to 4 centimeters, and the angle between those sides is 50 degrees. Because these conditions satisfy SAS, the two triangles are congruent. Quick insight: SAS works only with the included angle. If you mistakenly use an exterior angle, the rule doesn't apply. So always check carefully where the angle lies. That's the beauty of SAS, a neat and reliable shortcut to prove triangle congruence. Hello everyone. Let's dive into an exciting property of vertically opposite angles and see how congruence helps us prove even more. Take a look at the figure. We have triangle AOD and triangle BOC. Notice that side OA is equal to side OB and side OD is equal to side OC. Also, angle AOD is equal to angle BOC because they are vertically opposite angles. Now, with two sides and the included angle equal, we can say by the side-angle-side rule that triangle AOD is congruent to triangle BOC. Once we know the triangles are congruent, corresponding parts must also be equal. That means angle OAD is equal to angle OBC. And from that, we can deduce that line AD is parallel to line BC. So the key takeaway is this: congruence doesn't just prove triangles equal, it also helps us establish parallel lines and equality of other corresponding parts. Isn't that powerful? Hello everyone. Let's explore an important property of perpendicular bisectors. Imagine line AB with midpoint C. Now we draw a line L, which is perpendicular to AB and passes through point C. Take a point P on this line L now. Look carefully at triangle PCA and triangle PCB. Here, side AC is equal to side BC because C is the midpoint. Angle PCA is equal to angle PCB, both being 90 degrees. And side PC is common to both triangles. So, by the side-angle-side rule, triangle PCA is congruent to triangle PCB. And once they are congruent, corresponding sides must be equal. That means side PA is equal to side PB. The key takeaway is any point lying on the perpendicular bisector of a line segment is always equidistant from its two endpoints. That's why this rule is so useful in constructions and proofs. Let's dive into another important criterion of triangle congruence, the angle-side angle or ASA rule. Think about this: if in two triangles, two angles and the included side are equal, then the triangles are congruent. That means their shapes and sizes are identical. For example, consider triangle ABC and triangle DEF. If angle B is equal to angle E, angle C is equal to angle F, and side BC is equal to side EF, then triangle ABC is congruent to triangle DEF. This is summarized in Theorem 7.1. Notice, the proof of ASA actually comes from the side angle side rule applied across different cases. That's why ASA is a theorem, while SAS is taken as an axiom. Here's a nice shortcut insight. If two angles of a triangle are equal to two angles of another triangle, the third angle is automatically equal to. So, verifying just two edges and the included side is enough. So to wrap up, the ASA criterion is one of the most practical ways to check congruence, quick, logical, and very often used in geometry proofs. Alright students, now that we've seen the ASA rule, let's carefully prove why it always works by analyzing different cases. We are given two triangles, triangle ABC and triangle DEF, with angle B equal to angle E, angle C equal to angle F, and side BC equal to side EF. The target is to prove that triangle ABC is congruent to triangle DEF. Let's start with case 1. If side AB is equal to side DE, then directly by the side angle side rule, the triangles are congruent. Simple and straightforward. Now, case 2. What if side AB is greater than side DE? In that situation, we choose a point P on AB such that PB equals DE. Then, we compare triangle PBC with triangle DEF. They turn out to be congruent. But this creates a contradiction unless AB actually equals DE. And finally, case 3. If side AB is smaller than side DE, then we choose a point M on DE such that ME equals AB. This simply reduces the situation back to case 2. Therefore, in all possible cases, triangle ABC is congruent to triangle DEF. So, this proves that the ASA criterion is always valid no matter how we look at it. Let's now talk about another very useful congruence rule, the angle-angle side criterion, or simply AAS. Imagine two triangles where two angles are equal and one side corresponding to those angles is also equal. In such a case, the triangles are guaranteed to be congruent. Why does this work? Well, remember the angle sum property of a triangle. The sum of the three angles is 180 degrees. So, if two angles are already equal, the third angle is automatically forced to be equal as well. This makes AAS almost a natural extension of the ASA rule. That's why AAS is widely used to prove congruence in problems where we know two angles and one side. For example, in the diagram, you can see pairs of right triangles with equal angles and sides, and hence they are congruent. Quick insight here, AAS is nothing but a direct consequence of the angle sum property, and it saves us from having to check the third angle explicitly. So, whenever you find two angles and a side equal, you can confidently conclude the triangles are congruent. Let's bring it all together. Not every equality ensures congruence. A single side or side plus angle is insufficient. But the reliable rules are SAS, two sides and included angle equal. ASA, two edges and included side equal. AS, two angles and one corresponding side equal. Once triangles are congruent, we can use CPCT to deduce further equalities like sides, angles, or even parallel lines. And that's the beauty of triangle congruence. It gives us powerful tools for reasoning in geometry. In the next video, we'll take this one step further and explore a very special rule for right-angled triangles, the RHS congruence rule. Stay tuned because that's where things get even more elegant.